Welcome to another edition of Physics Videos. Our topic for today is thermodynamic cycles. You may recall from a previous physics video that we can monitor how the state of a system of molecules changes by creating a pressure-volume diagram. We also looked at 4 different thermodynamic processes, ways in which the state of a system can change. Today we'll look at several processes in succession. Suppose we take a system at pressure P1 in volume V1 and let it change by doing an isobaric expansion to a new volume, V2. It might look something like this. We'll use the letters A and B to represent the beginning and ending states for this process. Recall that in this process the temperature increases and positive work is done. The work is found by calculating the area beneath the line connecting A and B. Now, let's suppose that the pressure is decreased to P2 at constant volume, an isochoric process. It will look like this. This process does no work, however, the temperature and internal energy of the system decrease as we move from state B to state C. Now, let's compress the gas from V2 back to V1, keeping the pressure at P2. It will look like this. This process lowers the temperature, and does negative work equal to the area beneath the line from C to D. The cross-hatched area represents negative work and reduces the work that was previously done to expand the gas. Finally, let's add one more process to bring the gas back to its original temperature, pressure, and volume. This will require an isochoric process to raise the pressure to P1. Just like moving from B to C, moving from D back to A does no work, but the internal energy and temperature increase. We have taken our system through 4 different processes, but have returned to the original state. Any sequence of processes that returns to the original state is called a cycle. Now, let's analyze the entire cycle. The first thing to look at is the total work done. The process from A to B does positive work, the orange area. And, the process from C to D does negative work, the cross-hatched area. So, the total work done during the cycle is the orange area minus the cross-hatched area. But, what is left is exactly the area contained inside the cycle. This will be true for any cycle we may draw. In addition, because the cycle begins and ends at the same temperature, the change in internal energy for any complete cycle is 0. These arrows show whether thermal energy is added to the system, labeled as Q in, or is taken out of the system, labeled as Q out. From A to B, there is positive work and a positive change in internal energy, so, the first law tells us we must add thermal energy, Q is positive. From B to C, no work is done and the change in internal energy is negative, so, the first law tells us we must remove thermal energy, Q is negative. From C to D, the work done is negative, and the change in internal energy is negative, so, the first law tells us we must remove thermal energy, Q is negative. And finally, from D back to A, there is no work done and the change in internal energy is positive, so, the first law tells us that we must add thermal energy, Q is positive. For the entire cycle, the net thermal energy needed is equal to the net work done during the cycle. This is because the net change in internal energy is 0. The last thing to look at is how efficient our cycle is. The goal of creating a cycle is to have it do work. If we think of our cycle as operating like a machine, there is a need to reset the machine during each cycle. To do this we must exhaust some thermal energy. However, this means that some of the energy that we add cannot be converted to work. So, our machine cannot be 100% efficient. We define efficiency as the ratio of useful work output divided by the thermal energy we add to the system. The symbol we use for efficiency is the Greek letter, eta. It looks kind of like a script N. Here is the equation for the efficiency of a cycle. Since the net work done is the difference between thermal energy transferred in and thermal energy transferred out, we can substitute for W in the equation. If we divide through by Q in, we get the final result. Efficiency is 1 minus Q out over Q in. Now, let's summarize what we've learned. For any thermodynamic cycle, the net work done is the area inside the cycle and the total change in internal energy is zero. In addition, since the change in internal energy is zero, the work done must equal the net transfer of thermal energy. And finally, the efficiency of the cycle is 1 minus the ratio of thermal energy removed to thermal energy added. In another physics video episode, we'll take a look at a special thermodynamic cycle. It is called the Carnot cycle. We'll see why it is so special.
Until next time, bye-bye.